Hello guys, I am Harsh and I have taken this initiative to discuss some of the problems from various coding platforms such as Leetcode, Codeforces, Spoj, etc. And in this series, the first problem which I will be discussing today is the minimum height trees. So just now read the problem statement. A tree is an undirected graph in which any two vertices are connected by exactly one path. In other words, any connected graph without simple cycles is a tree. So this paragraph just gives me a basic description of what is a tree. Any connected graph without simple cycles is a tree. Given a tree of n nodes labeled from 0 to n minus 1 and an array of n minus 1 edges, where edges of I is equal to ai, bi indicates that there is an undirected edge between the two nodes ai and bi in the tree. You can choose any of the node as the root. When you select a node x as the root, the result tree has height edge. Among all possible rooted trees, those with minimum height are called minimum height trees. Return a list of all minimum height trees root labels. You can return the answer in any order. The height of a rooted tree is the number of edges on the longest downward path between the root and the leaf. So this is the problem says that we are given n nodes in the tree and which are labeled as 0, 1, 2, n minus 1. Now just try an example. Suppose suppose n is equal to 4 and we have the nodes as follows: 0, 1, 2 and 3 with the connections as such. The question says that in this tree we can consider any of this vertex or node as the root of my tree and then calculate the height for each rooted tree. And among all those rooted trees, the tree which gives me the minimum height is the minimum height trees. So as an answer, I have to return the root labels of those minimum height trees. So suppose in this example, the height when I will consider 0 as the root. So for in this suppose in this example, the height when I will consider 0 as the root would be 3. The height when I consider 1 as the root would be 2, and similarly for these two also. Now as we can see, the minimum height which we can get by considering all the rooted trees would be h is equal to 2. So as an answer, we will have to return 1, 2. So we can do the solution, and so this is a basic understanding of the problem. And if you try to think of a solution, what comes to mind is that we can iterate through each of these nodes, and for each node we can find the height of the rooted tree, and for each height we can map it to a set or an array of nodes which contains the root labels for that particular height. For example, suppose for height 3 we can map it to an array of root labels giving 0 and 3. For height 2 we can map it to an array of nodes containing 1 and 2. So in the end, after iterating through each of these nodes and then suppose doing a DFS search DFS approach, and then finding the height for that rooted tree and then getting this map, we can just return the array corresponding to the minimum height as my answer. Okay. So but the problem here is that since we have to iterate to each through each of these vertices and then do a DFS on that, suppose, so the time complexity of the solution would be big O of n square. But unfortunately this gives us TLE and the solution is not acceptable. So now what do we think now, like what can be our approach to optimize the solution and get the appropriate answer? Now just try another approach. Suppose we have these 4 nodes, 3. So we want those nodes which gives me the minimum height. So what if we eradicate each of these leaves nodes from my graph? Will we lose any of my root labels which are in my answer? No, because we can see that the leaves of the graph will always give me a height which is greater than the least height um, of my answer. Like so, we can say that the leaves will never be in my answer, only except from the cases when we just have 2 nodes or 1 node. In case we have just 2 nodes, so these both will have a height equal to 1, and 0 and 1 should be in my answer. In case we have n is equal to 1 and we just have 0, then this should be my answer. But when we have 3, we can say that we can just eradicate these leaves, and then this will be my answer for my question. So what I'm trying to say here is that if we get a graph, if we get a tree, then instead of iterating to each of these vertices, to each of the vertex, and then doing a DFS search in order to get the height, we can just keep on eradicating, keep on deleting the leaves from my graph, and then getting a new graph. And we will keep on doing this till the value of n is greater than 2, because as soon as the value of n is less than equal to 2, we correspond to any one of these cases. So this is our approach of what we'll be doing. Now just consider one more example so that we can get a clearer understanding for this. Suppose we have the nodes as such. So writing the heights for each of these nodes would be so. As we can see, the minimum height which we get from the rooted trees is h is equal to 2. So my answer should contain 2 as the 2 in my array. Now just let's try it with the approach which we just discussed. Is that we will keep on deleting the leaves from my graph and getting my new graph, and I'll get a new graph after deleting the leaves. We will again delete the leaves. We will again delete the leaves if the value of n is greater than 2. So since the value is greater than 2 now also, so we can delete these 2. So in the end, when the value of n goes below 2 and when the value of n is less than equal to 2, so that will be my answer. So we can consider it for many different test cases. Suppose the example given in this problem is we have 1, 0, 2 and 3. So as we said that we have a what the leaves of my current graph would be 0, 2 and 3, and the current value of n is equal to 4, which is greater than 2. So since the value of n is greater than 2, what we have to do is we have to delete the leaves from my graph. So after deleting the leaves from my graph, the value of n becomes 1 and my new leaves becomes 1. Now since the value of n is less than equal to 2, we can return this array of 1 as my answer. So this is the approach, and now just let's try to code the solution. So we will be needing an array of leaves to contain the leaves which would hold the leaves of my current graph. I will also need an array of named as degree, which will contain the degree of each node, which would help me to identify the leaf nodes, because we know that when degree of a node is equal to 1, that is a leaf node. And then we will contain the information about my graph in an unordered map, in which we'll map the key to an unordered set of integers, which would represent the nodes which are connected to that particular node. And then now let's just create the adjacency map. Suppose since this is an undirected graph, we have to do this from both the sides. So after adding the information of the edges in my adjacency map, we'll also have to update the degree of each node, such that if we are adding one edge, it means that the degree of each of the node uh, containing that edge should increase by 1. Okay, so now we have our map prepared, and now what we want is we want to update this array of my graph, which will contain the leaves of my current graph. And as we know that our current graph has all the nodes which are given to us. So now we'll just iterate through each of the nodes and check if the degree of that particular node is 1. It means that it is a leaf node, and in that case we will push it to the leaves array. So now we have also got the updated the leaves array, we have updated degree, and we have also created the adjacency map. Now let's just handle one corner case, is that suppose when n is equal to 1, we know that we just have to return a vector which only contains 0, because in that case that will be the only answer. And then we will also create a new vector, a temporary vector, to let's say, which is new leaves. This vector will contain the new leaves of my graph. Like when I'll delete, suppose this is my graph 0, 1, 2 and 3. So if I delete the leaves from my graph, my new leaf would become 1. So this new leaves will contain 1, and after every iteration I will update leaves. So I just run the loop that while n is greater than 2, we will have to keep on deleting the leaves from my current graph and making a new graph, and then assigning that new graph as my current graph. If the value of n is less than equal to 2, then we just return the leaves as my answer. If it is not, then we'll keep on deleting the leaves from my graph. So when we delete the leaves from a graph, then the value of n reduces by the number of leaves. Okay, and so now we will iterate Now we'll iterate to each of the leaves. Then update the now delete the leaf from my graph. So when we delete the leaf from my graph, what would happen is that suppose we have my graph as such. So when we delete 0 from my graph, the degree of 1 would go from 3 to 2. And also in my map, I was containing information like 0 was containing a set of 1, 1 was mapped to a set containing 0, 2 and 3, 2 was mapped to a set containing 1, 3 was mapped to a set containing 1. So when we delete 0, here we had 0. When we deleted this, the degree of 1 would change, and also we'll have to erase this and also erase 0 from this particular set. So when we delete a node, we'll have to make these changes. So let's just get hold of that leaf node in a variable current. Okay, and now we'll go to the neighbor of my leaf node, and we'll just erase current from the set of the set which is mapped to the neighbor, right? And also we will decrease the degree of neighbor by 1, and we'll also keep a check here, like if the degree of neighbor equal it becomes 1, then we'll push it into my new leaves array. Okay, so we are erasing the leaf node from the neighbors set, and we are also decrementing the degree of the neighbor by 1. If the degree becomes 1, then we will just push it to my new leaves, and we will do this for each of the leaves. At the end, what will happen is we have deleted all the leaves and updated our degrees and updated the map accordingly, and now the new leaves will contain now contain the leaves of my new graph. Okay, so now just update my leaves array, which will be equal to new leaves, and also my new leaves should get empty. We are initializing the new leaves again as an empty array here, and so this is it. This loop will keep on running till the value of n is greater than 2, and when we get out of this loop, like when the value of n becomes less than equal to 2, we will just return the leaves of my current graph, which is after deleting all those leaves from my previous graphs. Okay, so let's go through the solution once again. This is an array of leaves which contain the leaves of my current graph, and this is the array of degree which contains the degree of each node, and it keeps on updating as we delete leaves from the graphs. And this is a map which contains information about the graph. Here we update the informations in the map, and then we update the leaves array initially to contain the leaf nodes of my initial graph. If the value of n is 1, we just return a vector containing 0, and then we create a new leaf vector here, and we iterate this loop while the value of n is greater than 2, and we keep on decreasing the size of n by leaf dot size, which means that we are deleting the leaves from the graph, and Then iterating through each of those leaf nodes, we delete that leaf node and we also update the degree and the set map to that neighbor. And if the degree of the neighbor becomes 1, it means that in my new graph, that neighbor will be my leaf node and we'll push it to the new leaves. And after that, we just update my leaves here, and then we also make my new leaves again as an initialize new leaves as an empty array again. And in the end, when we get out this loop, we can just return leaves as my answer. Just let's try to run this code. Yeah, it works. Let's try to submit it. Yeah, it works. So this was my solution, and in case you have any doubts or any improvements you would like to suggest, you can put that in the comment box. I will go through that. And thank you so much for keeping up with me till here. I hope you liked it.